This is the Bambu Lab H2C, with a bold claim to make multicolor printing faster and less wasteful. This 3D printer has a rack of 6 individual nozzles on the inside, which it can switch between, and they heat up within seconds thanks to induction. But is this really the next big thing? In today's video, we'll take a look at Bambu Lab's new Vortek system, dive into the engineering behind it, and compare it to other popular tool changing solutions on the market. Let's find out more. Guten Tag everybody, I'm Stefan and welcome to CNC Kitchen. This video is sponsored by Voxel PLA. Is this video too long for you? Here's a TLDW for the impatient. Everyone else can look forward to a deep dive into the system after that. If you appreciate that, consider leaving a like. So, what is the H2C? In specs, it's almost identical to the dual nozzle printhead H2D, where the left nozzle can be lifted and lowered. However, the right one can now be automatically switched during printing. A nozzle rack on the inside of the machine holds up to 6 hot ends, so when you change from one to another color, you don't have to flush all of the old filament out, creating the infamous poops. You simply pick up a dedicated hot end with that color and continue printing. Is it really waste-free? No, it's not, because you cut the filament, you first need to push the new filament into the melt zone to essentially melt the ends together so that you can retract, which is important for printing, and you also need to purge out some or all of the material that has been sitting in the melt zone for a while and doesn't simply print well anymore. That's why you still have a purge tower, but the size is very comparable to what you also see on Toolchangers. How fast is it? Because it still uses the AMS system when changing nozzles, it needs to retract the filament into the box and then feed new filament into the hot end. Including purging, this takes around 40 seconds compared to the 10 to 15 seconds on a tool changer. Though this is still by far faster than on a single nozzle system, when a change can easily take 1 to 2 minutes. So depending on the model you print and the number of colors or materials, the print time is around 50 to 100% slower than on a tool changer. But if you print with only 2 materials, only the left and right nozzles are used and no filament needs to be retracted, leading to print times just as long as on a tool changer. How many colors can you print? You have 6 swappable nozzles and 1 fixed, which makes 7 colors without any nozzle purging. But you can print with up to 24 colors or materials in total if you are okay with a combination of nozzle changing and nozzle flushing. Any print with more than 5 colors will require at least 1 additional AMS though. That's all handled by the slicer, and it will also tell you where to put the filaments to waste as little material as possible. How fast is induction heating? It's really fast. It takes below 10 seconds to heat the nozzle to PLA temperatures, where a normal hot end takes around 40 seconds. But I'll do a deep dive into the new nozzles later. Do you lose printing space due to the nozzle rack? Yes, the print area is 20mm narrower, and unfortunately the H2D and H2S print plates don't fit the H2C. How much does it cost? At the time of the release, the H2C is $2,399, which is only $100 more than the MSRP of the H2D. But since that usually sells for less, a realistic price difference is around $400, with which you get the additional tech and nozzles, and you also get the new advanced toolhead fan that currently is only on the H2D Pro. There will be an upgrade kit for the H2D and the H2DS out in Q1 2026, but I don't have any information on how much that will cost. The H2C and also the combos with the laser units are available now in local warehouses all around the world, besides the USA again. But since the US shutdown finally ended, it might also be available there very soon. To check current prices and availability, consider using the links below that also support the channel. My trial by fire for the H2C was printing another Majora's Mask by 3D Print Dogs. I used 8 filaments in total, the whole print took 2.5 days and switched filaments 3,600 times. And even though that sounds like a lot, it only took half the time and produced 7 times less waste than my first attempt on the X1 carbon. The results look so good, not only because of the printer, but also thanks to today's video sponsor Voxel PLA. Their filaments are some of the most affordable yet reliable on the market, and this print is a great example of that. They offer a wide range of colors that work flawlessly with any multi-material system, and they even offer free same-day shipping in the US on orders over $75. Despite their name, Voxel PLA also sells PETG if you need a bit more temperature resistance. But what I really love are their 3D printer accessories. Not only do they offer the X filter for the old P1 and X1 Bambu Lab printers, but since the H series still doesn't filter the exhaust when printing PLA or PETG, their Vento H2 filter is here to solve that by simply screwing onto the back of the machine. Voxel PLA offers a special discount for the holiday season. So if you want to stock up on filaments or get some cleaner air in your workshop, you can get 10% off orders over $100 when you use Xver's Kitchen at checkout. Thanks to Voxel PLA for sponsoring this video. So let's continue with a deeper look at the H2C. And trust me, it's interesting if you love tech. First of all, I need to say that I love the new look, whereas the H2D had the light gray panels, the H2C has these nice dark gray ones that simply look better. But the interesting stuff happens on the inside. So let's take a look at the choreography it performs when changing nozzles. Okay, let's look at this a bit slower. First it cuts the filament and retracts it to the AMS. Then it starts the nozzle changing procedure by moving to the pin station. The rack actuates the pin so that the unlock mechanism can be triggered. Then the printhead moves back to release the tension and the nozzle rack lowers. The printhead then moves to a free nozzle station where the nozzle gets magnetically docked. After that, it moves to the station where the new nozzle is. The rack lifts and inserts the nozzle into the printhead, where it's temporarily held by a magnet. The rack lowers and the printhead travels to the pin station, where the locking mechanism is pushed in again to lock the nozzle and securely pull it into the taper that ensures that the nozzle is precisely at the same height and exactly at the same position every time. At that point, the induction heater kicks in to get the hot end to printing temperature. During the changing procedure, the AMS has already retracted the old filament and started loading the new one, which usually arrives at the new hot end a little bit after the procedure is finished and the nozzle is back to temperature. It then purges out some filament to establish nozzle pressure and remove some of the already degraded material onto the purge tower and continues printing. The nozzle changing procedure itself doesn't even take 15 seconds. The rest of the time is spent waiting for the filament from the AMS to arrive, which is almost an idle time of 20 seconds. Then there are around 10 more seconds to purge the filament onto the tower. So right now, AMS loading and unloading is definitely the bottleneck, and I don't know if they are able to improve this time significantly. My AMS is actually already full of shaved off filament that I'm worried might jam something at some point, so they might already be pushing the machine as hard as they can. A way to make the nozzle changes faster might be to reduce the length of the PTFE tube, but I haven't tried yet how much time that would save, and that would also ruin the compactness of the system. Something that's definitely not the bottleneck are the new induction nozzles. Yes, the H2C uses a completely new type of hot end, where there are only a few others on the market right now. This hot end doesn't heat with a resistive heating element, but by induction. You might know that from your stove. A high-frequency magnetic field causes metals, especially ferromagnetic metals, to heat up by inducing eddy currents and also magnetic hysteresis losses. So the printhead of the H2C features a chunky electromagnet on the right side with a C-shaped core. The nozzle gets placed within the air gap of this core and is exposed to the rapidly changing magnetic field. Induction heating is fast, and the new nozzles heat up to PL8 printing temperatures in under 10 seconds. That's 4 times faster than a conventional hot end. And this is important. Since nozzles cool down when they are in the rack, you need to heat them up as fast as possible once they are installed, because you can't preheat them like on a normal tool changer. The docks might look as if they are powered, but I think this circuitry is only there to detect if a nozzle is installed or not. But heating isn't the only thing a hot end needs to be capable of. You also need to sense its temperature so that the printer can precisely regulate it. Bambu Lab solves this problem by using a wireless connection between the hot end and the tool head, which is interesting and also a bit concerning at the same time. So let's take a closer look at the new hot ends. On the bottom, there's a hardened steel nozzle tip followed by a tiny silicone sock, probably preventing excessive material buildup. Then there's a taper that locates the nozzle during every changing procedure. After that follows the melt zone, which we'll take a look at in a bit, because I disassembled one out of curiosity. On the top, there is an aluminum heatsink, and on the top of that, there's a small PCB where the wireless magic happens. The first thing you can spot are two coils, of which one is probably for transmitting power, just like your wireless phone charger, and the other one for transmitting data. Keep in mind that these coils only need to transmit tiny amounts of power, because this circuitry is not for heating. That's done wirelessly by the beefy coil on the print head. They are just there for sensing the hot end temperature. There aren't a lot of components on the PCB, and only two QFN packages really stand out, as well as one SOT component. Everything is covered in silicone for protection, but it's easy to scrape off, and I wouldn't have expected that the components are really labeled. I'm not an electrical engineer, so if you have more insight on what the components do, please let us all know in the comments. The one chip on the right is labeled FM1230, which seems to be an authentication chip common in QI charging standard and might be used to make sure that the nozzle you're using is a genuine Bambu Lab nozzle. This is complete speculation, but that could be a big hurdle for third-party manufacturers if they don't get the PCBs from Bambu Lab. The other chip is labeled GDE23SFA, and I couldn't find anything about it online, but I suspect it's a small microcontroller that reads the two temperature sensors on the hot end, sends the data to the 3D printer, and will also contain information about what kind of nozzle it is. I don't know what the component in the middle is, but I suspect it's a MOSFET for power regulation. The bottom of the PCB is only populated by some passives. As I said before, there are two thermistors connected to the board. One sits in the heat break and makes sure that the cold side is not getting too warm, and the other one is routed all the way to the lower end of the hot end and monitors the hot end temperature. It's exciting to see how much tech they're able to squeeze into this small hot end, but I'm also a bit worried about how much that will limit others in making third-party options. And with that tech and complexity, you would expect that the nozzles are quite expensive, but a normal nozzle only sells for $39 and a high flow one for $69, which is quite impressive. I also want to quickly talk about the induction heating part of the hot end itself. Bambu Lab are not the first to release an induction hot end. I actually have the Trident induction hot end from Plusmix running on my red rig, and we'll also see induction heating on the Vortek Index system. Since I wanted to know where and how Bambu Lab heats the nozzles, I sacrificed one and took it apart. First, there's an insulating sleeve around the melt zone. Under it, there's a clip. I thought at first that this was to hold the thermistor wire in place. Under it was a chunk of metal I assumed was steel, so it heats in the magnetic field. I was confused when I touched it with a magnet, and it wasn't magnetic. Scratching away some of the paint revealed something golden, and I suspected that this was brass. And since the hot end was already ruined, I took it to my belt sander and simply sanded away half of the hot end to find out how it really looks from the inside. And here it is! So the main part of the hot end is brass, because it's easy to machine and has good thermal conductivity. Only the tip of the nozzle is hardened abrasion-resistant steel. But if the upper part is brass, how does the induction heating work? First of all, induction heating also works with resistive losses caused by eddy currents in the material, but they are way lower than the hysteresis losses in ferromagnetic steel. This was also the moment when I understood what the steel sleeve is actually used for. I think its primary use is not only to hold the wires, but this is the main part that's heated by induction nicely all around the hot end. And the brass block below it will then distribute the heat into the nozzle and result in uniform and efficient heating. A very clever approach in my opinion, because I tested the Trident hot end 2 years ago, where only a thin metal tube is heated, and the heat distribution within the melt zone was one of its biggest weaknesses. For a good hot end, you want a very sharp transition between the hot melt zone and the cool side, so your material is either hard and can easily be fed, or molten. Anything in between just becomes squishy and causes problems. To confirm my suspicion, I put a thermocouple through the filament path all the way down to the nozzle, then pulled it out in steps and noted down the temperatures. And the temperature distribution was really nice. It starts a little low at the nozzle tip, simply because it's quite a bit away from the heated zone, but then rises to the set temperature and quickly plummets once the heat break starts. And this looks very similar to Bambu Lab's standard hot end that I tested in the same manner. It seemed as if the melt zone was a bit longer on the induction hot end, but when I did a flow rate test, the induction hot end performed a little worse than a regular hot end, with a maximum flow rate of 37 cubic millimeters a second instead of 41 cubic millimeters a second, which will probably not be noticeable in normal printing. The last thing necessary to have a reliable tool or nozzle changer is a way to align the nozzles. Even though all the parts are precisely manufactured, there are always tolerances. So if you switch from one nozzle to another, the nozzle orifice might not be at exactly the same location, which would result in different colors of your print not lining up. In the early days, we used to calibrate the offset via calibration patterns that you printed. The Prusa XL and the Snapmaker U1 probed their nozzles on a feature on the bed to measure the nozzle offset. The H2C uses, like the H2D, an eddy current sensor over which the nozzles get moved one after another to find their centers. The H2C does that if you don't deactivate it every time you start a new print. Unfortunately, this procedure can take a while. The complete print preparation with leveling takes around 15 minutes on a 4-color print, and when I printed Majora's Mask in 8 colors, it took over 20 minutes. This can be pretty annoying, but Bambu Lab prioritizes convenience and good print results over time. And this is also the same thing with filament purging. As I said before, this is necessary to push the new filament into the melt zone so that you can retract and also get rid of the old filament that might have already been in there for a few minutes and degraded. Initially, when we got the machines, the purge amount was very excessive. I had some conversations about that with Bambu Lab during the review process, and at some point they added an option into Bambu Studio to switch between standard purging and an eco mode. Standard is the conservative mode that should work with almost any material. Purge saving mode reduces the purge amount by a third, and from my experience works mostly well. I only had some models where the material were a bit too wet and my print temperatures were a bit too high, where I got significantly more stringing in this mode. The nice thing here is that it doesn't only reduce the amount of waste, but since purging takes time, it also reduces the nozzle change time by a few seconds. You can even remove the prime tower completely, but that will result in holes in your print where the extrusion starts. Working with completely dry material makes this a little better, but you don't reach the print quality of a print with a purge tower. I think you saw that the nozzle change time is quite significant on the H2C, but how does the print times compare to tool changers like the Prusa XL or the Snapmaker U1, single nozzle filament changers like the P2S, or a dual nozzle printer like the H2D? First of all, there is no precise single number that I can give you. It always depends on the size of your model and the amount of materials you use, but I'll demonstrate that at an example. The 4-color test cube, inspired by Extrudim's Mpox test cube, took 7 hours to print on the H2C in purge saving mode. The standard purging mode is, in this case, about 10% slower. Both tool changers were around twice as fast and printed the cube in less than 4 hours. Printing it on the H2D took around twice as long as on the tool changer, and it's only a little faster than the P2S because it doesn't have to change and flush the nozzle every time, but has those dual nozzles. Regarding waste, the results look different. The waste produced on the H2C is the prime tower, which weighs 23 grams compared to the 28 grams of the model itself. In normal purging mode, the prime tower is around 50% heavier. Since the tool changers prime as well, the weight of their towers was more or less comparable, with the U1 wasting a bit more. The H2D purges and flushes 8 times more material than the H2C because 3 of the 4 colors need to be flushed during a change, and the P2S is obviously the most wasteful with over 320 grams of poop and purge tower for a 28 gram print. We could discuss many more examples, but the exact difference in time and waste highly depends on the model. The thing that I want you to take away from this is that the H2C is slower than a tool changer because a nozzle change simply takes longer. But in terms of waste, it's on par because it also just purges the nozzle as tool changers usually do as well. That said, it is more efficient in time and waste compared to Bambu Lab's other machines because they need to significantly flush filament, which takes time and generates waste. The quality of the prints is very good in general, and I printed a ton of different multicolor models. The extrusions are clean and the layers mostly stack up nicely. The second multicolor bench bin that I printed turned out also significantly better, with only minor stringing, casters that stuck on the build plate, and all the mechanical functions worked nicely. The only thing that I noticed are some very slight imperfections every few layers, but only when you really look closely, and I think I had the same phenomenon on my H2D as well. This only happens if you print with different nozzles or tools. If you print with just one nozzle, the sides are very flat. And just as a comparison, the side surfaces of the same prints coming from the Toolchangers also have a slight texture. And once prints are bigger and more organic, the surface structure is not noticeable anymore. I had several multi-day prints and they all finished without any interference. But let's finally come to the maybe most interesting part. Who would benefit from the H2C? Who is it for? I mean, compared to a tool changer, it's significantly slower and also still generates waste. And for the price of one H2C, you can get 2.5 Snapmaker U1s. But where does it make sense as well? First, there's scalability. The U1 only prints 4 materials at once. The XL, 5. The H2C can print with 7 materials in nozzle changing mode, or if you are okay with purge waste, you can add multiple AMS units and print with up to 24 colors or materials at the same time. The other point is convenience. The H2C comes in the box with 4 0.4mm and a 0.2 and a 0.6mm nozzle on the nozzle rack. So printing with a different nozzle size is as easy as selecting a size within the slicer, and the H2C will pick up the right nozzle before the start. Yes, nozzle swaps are mostly easy and convenient these days, but I rarely find myself really changing them because I need to walk into the studio, change it, print with it, and then remember to switch back before I start the next print. The other convenience factor is that Bambu Studio is really good at optimizing your multicolor prints. You just load the model and the slicer will tell you where to load the materials so that it prints the fastest and with the least amount of waste. And this works so well that I didn't have a single failure or problem during the over 200 hours of printing, besides the casters of the multicolor bench bin not adhering to the bed. The machine and the ecosystem around it are designed so that even a non-expert can print such complex models without the slightest problem. Then there's capability. If you compare the H2C with the other 2 famous tool changers on the market, it's of course lacking in PLA multicolor printing efficiency, but once you go to technical materials, nothing beats the actively heated and compact chamber of the H2C. Tool changers simply have those big wiring looms on the top, which require ridiculous enclosures to house them, which makes heating a pain. The H2C still only has 1 tool head and the drag chain with the Bowden tubes that don't require any additional height. So if you plan to print technical materials, the H2C is simply a better choice. But why would you need a nozzle changer? Because you rarely print a nylon with PPS, ABS and polycarbonate at the same time. First again, different nozzle diameters that are directly available in the slicer. But the other thing is that Bambu Lab allows you to dedicate a material to a specific nozzle. I've shown in the past that you need to purge tremendous amounts of material if you switch from PLA to PETG, for example. Otherwise, the leftover of these materials on the nozzle will ruin the strength of your parts. It's even worse if you, for example, print at high temperature PPS and then want to switch back to PLA. The printing or changing temperatures for PLA are so low that the PPS won't even melt, and you first have to switch to a transition material like ABS before you can print with PLA again. If you have a dedicated nozzle for each material, you don't have to worry about that. And this also leads me to my conclusion. Yes, the H2D can do very nice multicolor printing, but so can the Prusa XL at a bigger size or the Snapmaker U1 at a significantly lower price. And those are even faster and produce less waste. So if you primarily want to do multicolor PLA printing or multi-material printing with PETG or TPU, they are the better choice. In my opinion, the Bambu Lab H2C with its Vortek system is not a revolution, but it's a solid and plausible addition to Bambu Lab's ecosystem. With only a bit of extra hardware, they made the H2 series more efficient without needing to develop a completely new platform. Many might have wished for a tool changer from them, but I'm in a way happy that they built a nozzle changer, giving us all another option and not resulting in Bambu Lab directly dominating another branch. The H2C can print almost any materials on the market and only struggles with soft TPUs. In dual nozzle mode, you can very efficiently print models with easy breakaway support. The nozzle changing system can print multicolor parts much more efficiently than their other machines. But I see its greatest benefit in convenience. Having a range of different nozzles available at the push of a button or dedicated nozzles for different materials. All of this fits in the same compact size as their other H2 series printers with an ecosystem around it that works just really well. For me, the H2C is an amazing, versatile business printer, but that comes at a price. If your budget is tighter, you don't need that convenience factor, or if you're not regularly doing complex multi-material projects, there are other more affordable options inside and outside the Bambu Lab ecosystem. But if you have the budget, the H2C is one of the most reliable and capable 3D printers currently available. I honestly had a really hard time making up my mind who would benefit from this machine and who not. But what are your thoughts on the H2C? Are you stoked to see this evolution, or are you disappointed by its performance? Let me know in the comments, and if you're in the market for buying one, then check out the links in the description that help me keep the lights on here in the studio. Thanks for watching, everyone. I hope you found this video interesting. If you want to support my work, head over to Patreon or become a YouTube member. Also, check out the other videos in my library. I hope to see you in the next one. Auf Wiedersehen and goodbye.